Okay, let's see if we can work another problem that you can approach through the point particle idea. And it's one that relates to some other topics that we've talked about recently, like angular motion and rolling. Suppose I have a yo-yo. Here's the yo-yo. It has a moment of inertia I and a radius r, and it's tied to a massless string. And I have it connected to the ceiling. And I let go of the yo-yo, and it falls down some height h. And of course, as it falls down, it starts to rotate as well as going downward. And the question I can ask is, what is the final velocity of that yo-yo after it's fallen a height h? And I'm going to approach this by looking at both the point particle view of this yo-yo and then in terms of the entire system, because there's not only translational kinetic energy, but there is rotational kinetic energy involved in this. So if I take the point particle approach, I would say that the change in the translational kinetic energy is equal to the sum of the external forces times the distance that the center of mass moves. Okay, and so this is going to be 1/2 mv final squared minus 1/2 mv initial squared. Now let's see what forces are acting on this yo-yo from outside. I should have the first step defined that my system is indeed the yo-yo, and so the forces that are acting on it are mg pulling downward, and then I've got the tension in the string that's pulling upward. And so the net force acting on this system, this point particle system, is going to be mg minus the tension and the distance that the center of mass moves is just going to be equal to h. Okay, so I've got this term goes to 0, so I can write from the point particle point of view that 1/2 mv final squared is equal to mg minus t times h. Oh, but I don't have enough information to calculate this because I don't know what the tension in that string is. Well, is there a way that I can calculate the tension? Let's see, I think what I can do is I can say that the change in energy in the system is equal to the change in energy, the change in the translational kinetic energy, plus the change in the rotational kinetic energy. We're assuming that there's no other energies involved in this. And that has to be equal to the total work done by external forces on the system. Okay. Well, I can, let's see, this is going to be the 1/2 mv final squared minus 1/2 v initial squared. This force, this tension force, is like the force that causes rolling. It is the force that causes it to roll, and at any point this tension force is not doing any work on this translational work on this wheel. There's no rolling or slipping, and so the external work done on the system from outside is just equal to mgh. That's a very subtle point. You've got to think about it. Remember when we rolled the disc down the inclined plane, we only worried about gravity and considering the energy. We didn't worry about the work, any work being done by the rolling constraint, because there is none. Okay, so this says that the rotational kinetic energy, the change in rotational kinetic energy, is equal to mgh minus delta k translational kinetic energy. The change in the rotational kinetic energy is just going to be equal to 1/2 I omega final squared minus 1/2 I omega initial squared. Okay. We started off without this rotating, so the initial omega for the yo-yo was 0, and so we get 1/2 I omega final squared is equal to mgh minus delta k translational. We still have too many variables, except that this is a rolling constraint problem, because that twine is just rolling off of the, the yo-yo is just rolling off of the twine. And so we've got the one other factor that we can add is that the velocity of the yo-yo is equal to omega, the rotational speed of the yo-yo, times r. Okay, so let's see. There's a lot of stuff in this. We've got the point particle system that says the change in the translational kinetic energy, the motion of the center of mass, is equal to this. So that's going to be mg minus t times h. Fine. We can look at the system as a whole. That means we have to take into account not only the translational kinetic energy of that yo-yo, but the rotational kinetic energy. And that's equal to the external work done in the system, which just turns out to be equal to gravity. And then we've finally got the rolling constraint. V is equal to omega r. So let's see how we can put all these together. All right. So I wouldn't mess up the calculation. I went ahead and did the whole thing from the start. If I have this yo-yo fall a distance h, the change in the translational kinetic energies is equal to mgh. And then I wrote down what those are. Remember, we started off with 0 velocity and 0 angular velocity, so we just end up with this. mgh is equal to 1/2 mv squared plus 1/2 I omega squared. And then I've got the rolling constraint that comes in here. Omega is equal to V over R. So I can plug that in. And so I end up with an equation that looks just like what we got when we rolled a disk down a hill, that the final velocity is equal to square root of 2 mgh over m plus I over r squared. So the velocity that you have at the end depends upon the moment of inertia of the yo-yo. If you've got a yo-yo that has most of its mass at the rim of the yo-yo, the moment of inertia is going to be larger, and your final velocity will be lower. There is one quantity that we haven't calculated yet, which is the tension on the yo-yo. So let's see how we can do that, going back to the point particle idea. We will assume that we've already calculated the final velocity. Okay, so let's assume that we've calculated the final velocity, the final linear velocity of this yo-yo after it's fallen a distance h. Then we can go back to the point particle model, say the change in the translational kinetic energy of that yo-yo had to be equal to the sum of the external forces times the distance that the center of mass moved. So there's the 1/2 mv squared. We just calculated v final squared, so we assume we know it. These are the forces that were acting upon the center of mass. We're not worried about what kind of real work they do. We're just worried that they exist. And here's the distance that the center of mass moved. So we had mg pulling down and the tension and the rope pulling up. So we know mg, we know the height, we know the velocity, which we calculated by looking at the change in energy of the entire system. So we can rearrange that, and we calculate then the tension in the rope. It's equal to 1/2 mv final squared minus mgh over h. Okay, now you think, gee, well, there's a whole lot hidden in there. All the stuff that was hidden in there came about from how we calculated v final squared. So you should go back through this little video and go back and review how we got that, taking into account the rotational kinetic energy and how that led us back to the tension. Cool.